So after understanding about the running time and the order of growth, let's focus on the next concept. Now this is fine. We know that for a program P we have different approaches and order of growths are there, right? So we generally describe those in a mathematical notation or in a different form, right? How do we give that time? Okay, this is okay. We found out that for a particular algorithm it is n square, and for a particular algorithm it is n cube, and we say this is the best algorithm, right? But to represent this as simply as n square as a number, it is not good. We have to give some approach that this is, it is p of n square, this is p of n cube, something mathematically we have to represent, right? For that we have something called asymptotic analysis. Okay. So what is this? Analyzing the running time of an algorithm for large input sizes, so that only order of growth of runtime is relevant. We understood that only order of growth is relevant criteria. Okay, right? So analyzing the running time of the algorithm using order of growth is called asymptotic running time of an algorithm. Okay, analyzing the running time of an algorithm for large input sizes, only assuming that only order of growth is the one which is helping us, that is called asymptotic running time of the algorithm. So we use some notations here in this asymptotic running time. Notations which we use to describe asymptotic running time of an algorithm is called asymptotic notation. Okay, asymptotic notations. Asymptotic analysis means trying to analyze the running time of the algorithms with respect to order of growth. That concept is called asymptotic analysis. Trying to analyze the running time of the algorithms. Yeah, we'll see more number of questions. We will see more number of questions. Trying to analyze the running time of the algorithm with respect to the order of growth is called asymptotic analysis. And we use some notations here. Those notations are called as asymptotic notations. Okay. What are those asymptotic notations? This is the most important. Again, this full concept of complexity analysis is very important for competitive exams, for gate exams, even for placements. Because they ask you what is the time complexity, which is the best time complexity, and different things. So we have some different notations. Okay, we have some notations here. We have total 5 different notations, right? What is the use of these notations? Again, I'll go back to our example. Program P, algorithm A, B, and C. We say its running time. I will not talk about running time now. I will talk about order of growth only here. I hope you understand how we got order of growth. Order of growth is derived from the running time, right? So the order of growth of this is n square, this is n cube, this is n factorial, for example, different cases, right? But we have to have some mathematical representation for this n square, n cube, n factorial. For that we have we say that the order of growth of algorithm A, order of growth of algorithm A is n square. We say the order of growth of algorithm B is n cube. Maybe why we have to study these notations, please understand. Okay, algorithm A, algorithm B used good data structures, to write the program. Here they have not used good the data structures to store the values and retrieve everything. So the time here, the time taken is n square, here it is n cube. There can be an algorithm which is nicely written by using perfect data structures like stacks, queues, or linked list, but the time order of growth is n cube. For B, they have not used anything. They have simply written in normal programming concepts, but the order of growth is n square. Till now we were simply playing, saying that whichever order of growth is less, that is best. So if I show you this data, you will tell n square is best, B is best, you will say. But the way it is written, this is best, right? To avoid this confusion, to avoid this, we have come up with same thing, same n cube, n square, we will represent them in different notations. Okay, these are the 5 different notations: big O, omega, theta, little o, and little omega. Big O, omega, theta, little o, and little omega. These are used for us to find out the order of growths. Order of growths, but with some notation. Okay, let's see what is this different notations. Okay, see, let maybe theoretically, if I explain with these definitions, you may get confused, but let's go through them, and we have beautiful examples like this to understand what is the asymptotic notations. Okay, don't worry, we have very good set of examples here to understand them. Okay, let us formally see the definitions. Let f of n and g of n be two monotonically increasing functions. Okay, let them be two functions. So f of n can be something like this: 7n square plus 3n plus 9. Okay, and g of n can be another function, 8n cube plus 9n. So we may have two different functions, f of n, g of n, like this. When you have two functions, f of n and g of n, we are trying to convert them, find out the order of growth. After finding the order of growth, we are talking about which is the best one, right? So assume that these both are having, these two are the functions. Okay, then we use big O notation. The definition of big O of g of n, we read it as big O of g of n. Big O of g of n. F of n is we say f of n is big O of g of n. Okay, when do we say this? That f of n is big O of g of n? Whenever, okay, all the functions with the lower or same order of growth as g of n. If the order of growth of f of n, the order of, no, this example you take, what is order of growth of f of n? N square. Order of growth of g of n? N cube. So it is clear that the order of growth of f of n, n square, is less than or equal to order of growth of g of n, that is n cube, right? Order of growth of f of n, that is n square, is less than or equal to, it is less than order of growth of g of n. Then we represent that the time complexity of this function f of n, the time complexity of this function f of n is order of g of n, means order of n cube. Okay, we say order of n cube. I'll repeat once again. There are a lot of if you understand one big O logic, you will understand all 5. Once you understand one big O logic, you will understand all 5. Let's see again. I'll repeat once again. So there are two functions, f of n and g of n. Its order of growth is n square. Its order of growth is n cube. Okay. So when you have a set of functions, when you have set of order growths like n square, n log n, n square log n, and so on. Okay, you have so many, there are different functions. The order of growth of one function is n, the other one is n square, the other one is n log n, the other one is n square log n, and so on, right? So when you have multiple functions like this, whose order of growth are n, n square, n log n, and so on, then we can say the time complexity, the generalized order of growth of all these functions is order of n cube. Why? All these are lesser than n cube. So these are functions f of n. These are the order of growth of different functions f of n's, and n cube is the order of growth of g of n. Okay. In such case, we say that the big O of n of g of n. Okay, big O of n square something. It means for that particular algorithm, your order of growth is less than or equal to n square. The order of growth of this algorithm, for this algorithm, if you find out the order of growth, it is, when you are using this big O notation, you are telling that this algorithm may take n or n minus 1 steps. Okay, it may take n and n minus 1 steps, right? Is it clear? Should I repeat once again what is big O of n? Students, should I repeat what is big O of n? Yes. Yes, I understand. That's why I said the complexity analysis concept is complex. It is difficult to understand. Yes, I'll make it, try to make it simple. Okay. Till now it was clear when we studied about running time and order of growth. Okay. Order of growth can should be represented. See, let me take this example. N2 plus sine n. N power 2 plus sine n. Okay, this is one function. You assume this as the running time. You assume this as the running time of the particular algorithm. Okay, n square plus 2n. Sin n square plus 2n, n power 2 plus sin n. This is an example. And we know the range of sine function is from -1 to 1. Is from -1 to 1. Okay, now you put -1 here. If you put minus, this is the running time of the algorithm. If you put -1 here, it becomes 2 power n minus 1, to n power 2 minus 1, that is n power 1, that is n. One case it is n, you put 1 here, it becomes n power 2 plus 1, that is n cube. See, for a certain input, it is n, for a certain input it is n cube. It means the order of growth of this function, the order of growth of n power 2 plus sin n depends on the input value. Depends on the input value. If I am giving a sine value as -1, this becomes n. If I give 1, positive 1, it becomes n cube. It means the order of growth of this function f of n is changing between n to n cube. It is changing between n to n cube. It means, it also means sometimes this function or this algorithm, sometimes it will take n time, n number of repetitions, sometimes it may take n square, sometimes 2n, sometimes so on, n power 2.5 and n cube. Same algorithm, it has varying time limit between n to n cube depending on the input. Okay, depending on the input, it has varying time limit n to n cube. Now, when you have varying order of growth from n to n cube, how do you generalize it? Is my question. What should be the order of growth? Should it be n? Should it be n cube? What should be the order of growth? Okay, I hope this example you understood. You have a function f of n, which is the running time of an algorithm, that is n power 2 plus sin n. N power 2 plus sin n. Okay, sin n value is -1 to 1. When I put -1, it becomes n. When I put 1, it becomes n cube. It means depending on the sign value, depending on the input value, the order of growth of this function f of n or the order of growth of the algorithm, it is changing between n to n cube. Sometimes n, sometimes n cube. So which one should I choose? Which one should be the order of growth of that particular function? Okay, for that we use some notations. When you have cases where the order of growth of a particular algorithm is changing. I hope you are understanding. I repeat once again. When you have an algorithm for which the order of growth or the running time function from which we derive the order of growth is changing depending on the input. Sometimes it is n, sometimes it is n cube. When there is different order of growth for a given function, how do we represent its order of growth? Now how will you compare? My question is here. Algorithm A, its running time is n power 2 plus sin n. Algorithm B, it is n square, or maybe if I put n cube. Which one is the best one? You have to identify whether A is best or B is best. We do not know. We cannot say this because at some case it is also n cube, this is also n cube. Okay, right? Maybe this is not n cube, it's also something like this. 2 plus some cos n is there, for example. We cannot change, we cannot say which one is best here. It may have different, it may have different values, it may have different values. So at different points we may get different no order of growths. To avoid this confusion, okay, when you have this kind of cases where a given function f of n is generating order of growth as n some cases and n cube some cases, it is better to represent them in a standard mathematical notation. Okay, how to do that? We have to use the asymptotic notations. There are 5 different asymptotic notations which will help us to represent the time running time or the order of growths of the algorithms. Okay, any doubts? Please tell me, is it clear now? Why are we studying about asymptotic notations? Right. In that concept of asymptotic notations, we have 5 different ways of representing. Again, I'll repeat. You have a algorithm A, its running time is n power 2 plus sin n, something like this. You have seen multiple examples, no? We have seen, see, this is the running time of a particular algorithm. This is the running time of a particular algorithm. Okay, if these are the running times, right, assume this is the running time of the algorithm. If I want to find out the order of growth for this, it depends on this sin n. It depends on this sin n. Okay, so sometimes it is giving n, sometimes n cube. It is difficult to generalize, so we have come up with some mathematical notations known as asymptotic notations. In that, the first one is big O. When should we use big O notation? When should we use big O notation? Big O notation can be used. Big O notation can be used if the running time or whenever the running time of the function, okay, running time of the function is varying between n to n square. For example, if the running time is varying between n to n square, okay, have the order of growth always as n square. Why n square? Because n is covered, n power 1.5 is covered, n square is also covered. Right? So we are trying to generalize it, taking the maximum one, taking the maximum value here. In that case, we have to use order of growth. Again, I'll repeat. Algorithm A, its values are changing between n power 0.5 to n power 1 to n power 1.5 to n power 1.85 to n square. At different times, the order of growth of this algorithm A is like this. These cases, sometimes n.05, sometimes n.15, 1.85 n square. Now, I want to have I want to compare this algorithm A with another algorithm B. I want to compare algorithm A with another algorithm B. I have to generalize this into one form. For generalization, we can use any of these notations. For generalization, you can use any one of them. But everything has one specific significance. What is that significance? For big O, if you want to generalize this as big O, you have to take here whichever is the maximum bound. If you are representing that the order of growth of this algorithm A as n square, if you are saying the order of the final order of growth of algorithm A is n square, then you have to write big O of n square. Big O of n square means this what is this? This is order of growth. Big O of n square is the order of growth of algorithm A. Its meaning is that this algorithm A takes different times. It takes different order of growths at different time between 0 to n square. Sometimes n.5, n power 1, n power 1.5, n power 1.85, and so on. When you are writing that for a particular algorithm A, the time complexity or the asymptotic notation of that particular algorithm A is order of n cube, it means this program A, this algorithm A can take any value, less than n cube. Sometimes n square, sometimes n power 2.5, and even n cube also. That is the meaning of order of n cube. So you have to use big O notation. You have to use big O notation if the order of growths are less than or equal to n cube. So we can see n square, n. Is it clear? Order of, right? This algorithm A is taking n square, n power 2.5, n cube. It is changing at different points, different order of growth. So I am choosing, we can choose big O notation. We can choose big O notation in such cases. Okay, right? See here. See, example you see. The meaning of order of n square means if you are writing, if you are saying that the complexity of that particular algorithm is order of n square, when you are saying that the complexity of an algorithm is order of n square, it means that particular algorithm can have any of these times. It can have n square order of growth, n power 1.5 order of growth, 5, 200, 1, 3, n into n plus 1 by 2, log n, 8n square, anything is okay. We can say that it is order of n square. Why? Because the condition is f of n less than or equal to g of n. If the order of growth of the function f of n is less than or equal to order of growth of g of n, then we represent it as order of g of n. Okay, let's see the next one. I will make it very simple. F of n and g of n are two functions. Less than or equal to is this, greater than or equal to is this, equal to is this, strict less, strict greater than. That's why we have 5 different notations. Okay, less than or equal to, greater than or equal to. What if it takes only n square and n cube? Again n cube only. If you are using, see, one question somebody is asking, what if the algorithm A is taking n square and n cube time? Okay, n square and n cube time. If you want to use big O notation, then you can write order of n cube is the time complexity, is the complexity of this algorithm A. If you want to use big O, see, that is big O meaning. If you want to use big omega, you will write here like this, omega of n square you will write for the same algorithm. You will write omega of n square is the time complexity of this algorithm A. If you are using big O notation, you have to write n cube. If you are using omega notation, you have to write n square. Why? The condition, that's what I was about to explain to you. The condition of big omega is that this f of n should be greater than or equal to g of n. See, n cube, n square. If I want to use this omega notation, I have to write n square only, because out of these two, which one is less? N square is less. Then go for omega. Out of these two, which one is high? N cube. Then go for big O. So it depends on which notation you are using. It depends on which notation you are using. Okay, right? Yes, in big O, always consider the upper bound. In big omega, always consider the lower bound. Okay, in big O, always consider the upper bound. In big omega, always consider the lower bound. Right? So next, theta. When do we have to use theta notation? See, that's what. See, omega of n square means it can be n square, n 2.5, 2 power n, 3 power n, so on. It can take any value. We can generalize them and say it is big omega of big omega of n square. We can say omega of n square. Now, what is theta g of n? What is this theta? Here, we said that f of n should be less than or equal to g of n for big O. We said f of n should be greater than or equal to g of n for omega. The third case is theta. In this case, f of n should be equal to g of n. then we use theta. Okay, so see the example. You see, what is the order of growth of n square? It is n square only. What is order of growth of n into n plus 1 by 2? It is n square. What is order of growth of this? 8n square plus 9n plus 20? It is also n square. See, all of these are equal to n square. This is also equal to n square. This is also equal to n square. In those cases, you have to use theta notation. See the fourth one. Why is this equal to n square? How? 4 log n power 2 is can be written as n log 4 power 2, 4 base 2, which is nothing but log 2 square base 2. This is nothing but log n square. See, that's why it is n square. Some mathematical, some show off here to just represent this differently, right? 4 log n base 2 is nothing but n square only again. So we have to use theta notation when it is equal to case. Okay. Next, fourth one, small o. So big O is less than or equal to. Big omega is greater than or equal to. Theta is for equal to. Small o is strictly less and small omega is strictly greater than. Okay, see, small o of g of n. Okay, they should be strictly greater than. They should not be. It should be. There should not be an equal to case. There should not be any equal to case. It should be definitely greater than. It should be less than. Right? See, n power 1.5 is n square. 200 is n square. 1 is n square. Log n is n square, because they are all higher. This is higher always compared to all these things. Okay, that's why we have to use big O, and omega is for strictly less than. See, this should be smaller than all these terms. Okay, I already said this is little complex to understand, and you will, this is just a formal definition. I will now will play with numbers. Okay, it's my choice, right? I can, if somebody is representing the time complexity of an algorithm, yeah, we will see examples now. I will show you some good examples. These are some formal definitions, right? See, my goal was to compare which algorithm is best for a given problem. I had two algorithms, A and B. Okay, when you have two algorithms A and B, we found out order of growths. But order of growth has to be represented in some mathematical notation, either big O or omega. Then only I can compare. It. I can simply, I cannot directly compare n cube and n square. Okay, so that is little advanced, little adding more features to that order of growth. That is asymptotic analysis. Let's see examples. You when you play with numbers, you understand it better. Okay, I have some set of examples. I want all of you to please pay attention. This slide, if you understand, you understood asymptotic annotations. If you understand this nicely. Okay. So yeah, please tell me. You have to tell me whether these statements, which these are some true or false statements. Okay, these are some true or false statements. I will explain you one or two. See, given expression 8n cube plus 9n square plus 10n plus 20. The order of growth, how to find out order of growth? Ignore the lower order terms, ignore the coefficient of higher order term. Therefore, we get n cube. Okay. Now, this is order of growth. You know how to find it out. But there are some notations. We cannot, for program P, algorithm A has some order of growth n cube. Algorithm B also has some order of growth n cube. You cannot compare and say this both are equal. No, this is one more level of complexity. By seeing the order of growth alone, you cannot tell which one is best. You have to understand. We have to represent the notations and understand them. Okay, right? So first one example I will explain you. 8n cube plus 9n square plus 10n plus 20. This is the running time of an algorithm. Okay, instead of writing it simply n cube, I cannot write like this. For easy understanding, I told you have to write n cube like this. But actually, you have to use notations to represent them. You cannot simply write n cube like this. You have to use asymptotic notations. Big O, omega, theta, small o, and small omega. You definitely have to use them. This is for less than or equal to. this is for greater than or equal to, this is for equal to, this is strictly less, this is strictly greater than. Using this logic, let us try to solve this problem. See, here it is telling 8n cube plus 9n square plus 10n plus 20. The order of growth they are writing as big O of n cube. Is it true or false? Can we write like this or not? Can we write like this or not? How to tell whether can we write like this or not? How to tell that? Okay, so when you see, it is now you find out separately, you find out what is the order of growth for this. With my logic, it is n cube. No, it is n cube. So I can write order of n cube. I can write order of n cube because the actual order of growth is n cube. The actual order. So here f of n is n cube. G of n is also given as n cube. Okay, g of n is also given as n cube. I can use omega notation, big O notation. I can use big O because there is equal to symbol also here. See, less than or equal to. Therefore, this statement which I wrote here is true. We can write, we can give notation. You can write the order of growth of this function, first function, as big O of n cube. This is valid and true. Okay. I hope you understood why it is true. You see, this I will repeat the same 12 problems multiple times. Just focus on this, you will get the game. Second one you take, second one. It is given as belongs to. It is given as belongs to. We can use belong to also because this is a set. This is a set. Okay, the superset is order of n power 4. The superset is order of n power 4. Let me go with the problem, then come to this concept of belongs to. Okay, the problem is 8n cube, same question, 9 square plus 1. Is this true or false? Can we write like this or not? He has used big O notation. He has used big O. It means it should be less than or equal to. So the order of growth of this function 2 should be less than n power 4. Should be less than n power 4. What is order of growth of this? N cube. This is true, right? This is true. N cube is less than or equal to n power 4. That is true. Okay. Therefore, this is also true. We can represent the order of somebody wants to represent like this, belongs to order of n power 4. This is also true. Third one, see the third one, 8n cube, 9n square, so on, belongs to order of n square. He is given that order of n square. What is the order of growth of this side equation? It is n cube. I know it is already n cube. It is n cube. So is n cube less than n square? No, I cannot write. The meaning of he has used big O notation here. When he has used big O notation here, it means that when he has used big O notation, it means that the order of growth of the given function, of this given function, is greater than, it is less than n square. Okay, I'll repeat once again. When he has used this way, order of n square, he has given that it belongs to order of n square. It means that the whatever function is there on the left hand side, its order of growth is less than n square only. Only then you can use big O. Is it less than n square? Third condition, third question, is it less than n square? No. Why? We already know it is n cube. Therefore, this is false. We cannot write like that. Now, fourth one. Come to the fourth one. Okay. Again, this is fixed function, so it is n cube definitely. He has used omega means greater than or equal to. See, omega means greater than or equal to. Greater than or equal to. What term he has used here? N cube he has used. Is it true? N cube greater than or equal to is there. Therefore, it is true. Right? Fourth one is true. Next, fifth one. Let's see fifth one. Let me erase this. See the fifth one. Here he has used omega. He has used omega of n. He has used, and the omega means greater than or equal symbol. We have to put here. The time complexity or the order of growth of fifth function is n cube. Is it true? N cube greater than or equal to n. Is it holding true? Greater than or equal to n. Yes, it is true. It is true. Therefore, this is also true. You can ask me, sir, why are you studying all these things? Why different notations? Okay, for comparing two algorithms, okay, for a, you know bubble sort, right? You said you have studied bubble sort algorithm. You said you have studied bubble sort algorithm, right? You know this algorithm. Okay, for this, when somebody is asking, when somebody is writing its time complexity, or when somebody is telling its no running time or order of growth, somebody might tell you order of n cube, somebody might tell you omega of n square, somebody might tell you theta of n square. It can be valid in, they can write the time complexity of this particular algorithm in different forms like this, big O, omega, theta, like this. They can give these things. Okay, so based on that you have to compare. Don't simply see n cube and n square and say this is best. No, that's, I will teach you. There's one more concept left. There is just one more concept left. With that we will understand it fully. Okay, right. Sixth one, can you tell me sixth one is true or false? Students, tell me sixth one is true or false. He has used omega. Omega means it is greater than or equal to, we know left hand side is n cube, greater than or equal to n square. It is true. Sixth one is true. Sixth one is true. Why it is true? See, the order of growth of this is n cube. He has used omega means greater than or equal to, greater than or equal to. He has used n square. This is holding true, right? Next, tell me what about seventh one? Seventh one, is it true or false? Okay, why? Because he has used theta. Theta means equal to. It means the time complexity of this side function should be equal to this side function. Is it equal to? No. This is n cube and this is n power 4, not equal. This is false. Next, eighth one. Tell me eighth one. What about eighth one? True. Very good. Because this is n cube and n cube belongs to n cube. This is equal to, means belong to also can be used here. Okay, this is true. Ninth one. 9. Tell me ninth one. We have used small o. We have used small o means strictly less than. So this side it is n cube, strictly less than, this side also n cube. This is false. Okay, so ninth is false. Tenth one. Perfect. Tenth one true, because this side it is n cube and this is n4. N cube less than n power 4. Strictly it is less than. So this is true. 11th one. Omega means strictly greater than. It should be definitely greater than, should not be equal to. Right. This is also this is false. This is false, because this side it is n cube, this side is n cube, but it should be greater than. N cube greater than n cube came. This is wrong. It should be different. And 12th one, this side is n cube, this side is n square, and he has used omega. So it is strictly greater than. This is true. Okay, right? Understood this slide, all of you? Did you get the idea? How, what is the no, how and when are we representing the time complexity? Is it clear? Omega, big O, small omega, right? Now let me give you one very important point here. Okay, please just listen this one point. Our game is done. Okay, if you now you understood what is big O, omega, theta, small o, small omega, but there is one little flavor to be added. Let's see what is this. Okay, see, when are we actually using big O? You ignore these two. No, you talk only about big O, omega, and let's talk about only these three things. Okay, because this is less than or equal to, this is greater than or equal to, this is equal to. When do we use this big O? And when do we use this omega? If you observe, whenever I'm using big O, I'm focusing on the higher part. See, the second one, this case you take. Whenever I'm using big O, this side it is n cube, the left hand side it is n cube, but I'm representing it as an order of n power 4. Okay, order of n power 4, right? So I am focusing on the maximum side, I am focusing on the maximum value side, or I am focusing on the larger side, increasing order. I'll say increasing order. I'm using omega for decreasing order case. Decreasing, it means see, omega, here you wrote no, fourth one was true, and this one also true, sixth one also true. See, though it is n cube, we are writing n square. We are focusing on the lowest part here. We are focusing on the lowest order of growth. Here we are focusing on the highest order of growth, right? So omega is used when all the cases, maximum cases. Here we are taking decreasing case. Here we are taking equal to case. Now the point here is that if your algorithm, okay, if your algorithm, particular algorithm A, if you want to represent the worst case time, if you want to represent the worst case, then you have to go for big O. If you want to represent the best case, you have to go for omega. When you want to give average case, you have to go to theta. When you want to talk about average case, you have to go for theta. Okay, I will make it very clear with an example, right? So big O is for worst case, and this what we say, omega is for best case, and theta is for average case. Okay, so there are three different cases of no any problem. How has this three come? Let's talk about that. Okay, we will come to this example. I will come to that. Let's see the this part. I will, okay, let us go here only. Let's not go, we have so many things to discuss. See, linear search is a technique. Okay, you have an algorithm here. You have an array A with some elements 3, 5, 7, 9, 11, 13, 15, 17, and 19, indexing from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what is linear search? Linear search is a searching technique. Given array elements and given a key, okay, find out whether this key element is there in the array or not. That is linear search problem. What is linear search problem? This is an example problem I'm explaining to you. You have an array A with some elements. Okay, your target is to, and given a key, find out whether this key element is available in this array or not. You are searching whether the key element, this I will be giving you. Check whether it is available or not. How does this logic work? See, for I equal to 0, I less than n, end of the array, I plus plus, you have to write here if that a of I value is equal to key, the element is found. Is it not? I hope you are aware of this linear search logic. Linear search, right? What is linear search? Finding out whether the given key is available in the array or not. Now, suppose I give the key value as 5. If I give the key value as 5, how many times this for loop is running? One time it will go 0, that is 3. 3 is not matching with 5. Second time it will come here. 5 is matching with 5. Over. In 2 iterations, I got the answer that it is available. Okay. Take. Suppose if I give key value as 19. Suppose I give key value as 19. How many iterations it is taking? It will go for 3, 5, 7, 9, 11, 13, 15, 17, 19. Right? This will execute 9 times. Then I am able to find 19. Suppose if I give something between the key between 9 to 13, 9, 11, 13, if I give any of these things, it is taking some value between 3, 4, 5 or 6, something like this. So my key idea is to tell you here that if you are the same linear search algorithm, when you give the key value as 5, it is executing less number of times. When you give key value as 19, it is executing more number of times. And when you give the key value something between 9, 11, 13, it is executing some limited, some average number of times, 4 or 5 or 6, right? So that is the best case, worst case, and average case for the problem. For this linear search problem, given the key value, finding it immediately is the best case in low iterations, in less number of iterations. Okay, finding out the key in more number of iterations, it is worst case. You are able to find the solution for the problem in so many iterations. And for the third one, average case, it is taking some average value somewhere between 4, 5 or 6. Okay, so these are three different cases. Same problem, depending on the key, if the value is found quickly, it is best case. Why it is best case? Because less number of iterations. If it takes more number of iterations, it is worst case. See, you have to iterate the full array. You have to iterate the full array from here till here. You have to go 3, then 5, then check with 7, 9, 11, so on. Then you are finding 19. So after so many iterations, you are finding 19. Okay, this is a small array. Assume the case of 1000 array. Okay, assume the array size is 1000. Okay, beginning from 1 to 1000, for example. If the key is given as 1, quickly you get it. If the key is given as 1000, you have to iterate over the full array. That is the worst case. This is the best case. Average case can be anything in between. Okay, so to represent the time complexity of an algorithm, to represent the order of growth of an algorithm, in best case we go for omega. In worst case we go for big O, and the average case we go for theta. Is it clear? Understood, right? For the same algorithm, yes, we will understand it more. We have some more examples to understand. Don't worry, we will see multiple examples to understand when and where we have to use omega notation, theta notation, and big O notation. Okay, I hope this example cleared your doubt. This gave an idea. Now tell me which of these are true. Tell me out of 1, 2, 3, which one are true? You tell. Tell me out of this 1 to 5, which one are true? Tell me the numbers which are true. Left hand side is the f of n and right hand side is the g of n. Carefully observe the notation. Tell me out of these which are true. I am asking only true cases. Considering all things you say, considering everything you say. Okay, let me tell you one. Let me explain you one. You tell remaining. It is given as n cube equal to big O of n square plus n power 2 plus sin n. Okay, we already know this example, that it is varying from n to n cube. It is varying from n to n cube, right? So when it is varying, when I'm using big O notation, which one I have to use? N cube only I have to use, no? I have to use n cube. This is perfect. I would say that the order of growth is n cube, because I have used big O notation. It is no. See, this side it is varying from n to n cube. It is varying from n to n cube. But here it is n cube. Here it is n cube. And this side it should be less than or equal to, but this side it is varying between n to n cube. So sometimes it is n. So you take the best case. Suppose sin n value I am taking -1. This becomes n. So n cube less than or equal to n? No, it is false. So this is wrong. We cannot say this is true. Second one, let's take n cube equal to small o of n power 2 plus sin n. Okay, small o means strictly less than, right? So again, this case also, n cube is strictly less than order of n, because you put sin n as -1, this becomes n. This is also false. This is also false claim. Third one you take n cube equal to omega of n power 2 plus sin n. We know this is ranging between n and n cube, and he has used omega, so this should be greater than or equal to n cube. This case you see, n cube greater than or equal to n cube greater than or equal to n cube, both are true. Therefore this is true. Okay, right? And then fourth one, n cube, it is given as n cube equal to omega means strictly greater than, right? N power 2 plus sin n. So this value can be between n and n cube. So it is omega, means it should be strictly greater than n cube greater than n cube greater than n cube. No, here it is failing. So this is false. Okay. Next, theta notation. N cube equal to theta of n power 2 plus sin n. I know it is ranging between n and n cube. And here it is n cube. Here I use theta. It should be equal to. These two are equal, but these two are wrong. Therefore, this is also invalid. This is just an example to let you know how we are comparing, how are you using these notations, big O, when and where we are using big O, small o, omega, theta, and these notations. Okay, is it clear? You got idea? Anything you want to discuss, please let me know. Right, so these are few such examples we'll be trying to cover. These we will try to solve these examples. We will
You have 5 minutes remaining.
Okay, we'll try to see this in next session. So